Dear students, this class we are going to study about the bioactive synthetic polymers. So polymers are divided into different categories like synthetic polymers, bioactive synthetic polymers, natural polymers, and also the last one is microbial polymers. So here we have already studied about the biodegradable polymer films and coatings, and also synthetic polymers are also been covered. This class we are going to study about bioactive synthetic polymers. So this bioactive synthetic polymers are nothing but the polymers which are all derived from biological sources, but they are categorized as synthetic polymers. So bioactive synthetic polymers are synthetic polymers designed to actively interact with the food products by incorporating bioactive components like antimicrobial agents, antioxidants, or enzymes, often with the goal of extending the shelf life and enhancing the food safety. So these type of polymers are called as bioactive synthetic polymers. So they contains biological component into the system in order to extend the shelf life and the safety of the product. So examples of this bioactive polymer includes polymers like polylactic acid PLA infused with essential oils, polyvinyl alcohol with incorporated plant extracts, and modified chitosan with antimicrobial peptides, allowing for active packaging applications like controlling microbial growth and preserving the freshness of the food products. So these are all some of the examples of the bioactive synthetic polymers, and we are going to study the properties of these polymers. So this is normally a biopolymer. To the biopolymer, we are going to add some nanoparticles and active agents. This is nothing but these active agents or nanoparticles are going to improve the property of the polymer material. Okay, so when you use this, so when you mix all these things, you'll get a biopolymer complex, you'll get it, and composite you'll get it, and biopolymer active agents you'll get it. So these are all the different ingredients we can add along with this. So when you add a biopolymer with a biopolymer, you will get a complex biopolymer complex will get composite material, you will get it. And when biopolymer a nanoparticle is added with the biopolymer, you will get a bionanocomposite, you will get it. And then when a biopolymer is and active agents are added, you will get biopolymer active agents incorporated with the active agents, you will get it. Like this active agents may be of anything, like we can antimicrobial, antioxidant substances can be added along with that. So that is when you are adding all these things, what you basically we are doing is we are going to enhance the mechanical barrier and thermal properties of the food. So normally when you want to use these packaging material for food applications, we should have a very good mechanical properties, barrier properties, and thermal properties. You know very well that barrier properties are very much essential for fresh produce, because the oxygen water vapor transmission rate and OTR oxygen transmission rate are crucial for storing any food products which is packed using polymer packaging material. So when the oxygen transmission rate and water vapor transmission rate are higher, the product will spoil easily and it lose its integrity. So in order to prevent this, we have to choose a material which will have a low barrier property material, and also higher mechanical strength they should possess, and thermal resistance also should be higher in this case. So where we are going to use these materials, we are going to use to pack the fresh fruits and vegetables packaging, meat product packaging, dairy product packaging. We are going to use such kind of biosynthetic polymer material, and this material will enhance the shelf life and active properties of the materials. So types of bioactive synthetic polymers, aliphatic polyesters is the first one in this case. So the aliphatic polyesters are biopolymers which are all made up of repeating structures that upon degradation. So these are nothing but what they're aliphatic polyester material. These aliphatic polyester materials are actually biopolymers only. They have repeated structure. When they undergo degradation, they produce metabolites like poly beta hydroxyalkanoates and poly alpha hydroxyalkanoates substances are produced. So the biopolymer, when it undergoes degradation, it produces metabolites. These metabolites are called poly beta hydroxyalkanoates and poly alpha hydroxyalkanoates are produced, and they are easily biodegradable because of the presence of ester bond in the soft chain, making them sensitive to hydrolysis. Because ester bonds can be easily hydrolyzed, because of this ester bond, they can be easily degraded. That is the advantage of this one. These aliphatic polyesters have been used in commercial products as an alternative to the synthetic polyester due to their similar property, but they lack mechanical and thermal properties. Okay, so these polyesters are used when compared to that of the other polymer material. The polymer materials normally will have higher tensile strength, mechanical property, barrier property, but they will have lesser mechanical and thermal properties. Some of the aliphatic polyesters are used in food packaging or PLA, that is nothing but polylactic acid, polyvinyl alcohol, PEG. PEG is one thing, and PBAT and polyhydroxyalkylate PHA, polybutylene succinate and polyhydroxybutyrate and polycaprolactone are some of the materials which are all used. Okay. So the first of this category is, in this case, is polylactic acid, PLA. Polylactic acid has become one of the most significant commercial polymers nowadays that are biodegradable and bio-based thermoplastics option. Okay, so they are most significant nowadays. Many of the packaging material, they are using PLA as a basic raw material for the manufacture of this. PLA is made up of alpha hydroxy acid, which includes polyglycolic and polymandelic acid. So PLA is mainly composed of what? Polyhydroxy acid. What are all the polyhydroxy acid? One is glycolic acid and mandelic acid are the two acids which are used in this case for the manufacture of the alpha hydroxy acid, PLA. Okay, so PLA is derived by depolymerization of the PLA is derived by depolymerization of lactic acid monomer obtained from sugar, cane, cornstarch, or tapioca. So I told you already that these are all called as bioactive polymers. So biopolymers are nothing but what? The polymers, which are all, they are synthetic polymers, but they are derived from some amount of biological material will be there in this case. So here they are obtained by the depolymerization of lactic acid monomer obtained from sugar cane, cornstarch, and tapioca. So the sugarcane, cornstarch, and tapioca, it contains starch molecules, more of starch, and they undergo depolymerization. They'll form lactic acid, and this lactic acid is a basic for the PLA. These biopolymers are used in a wide variety of industrial applications such as disposable household items like drinking cups, cutlery trays, food plates, and containers, food packing, waste bags, shopping bags, agricultural, soil retention, sheeting, and agricultural films are made from PLA only, and drug delivery systems and biomedical devices are made from this polylactic acid materials. So PLA is used in commercial food packaging manufacturing, caps. That is, it is used in the food packaging, commercial food packaging for the manufacture of caps, PLA blends, coffee capsules, pouches, coffee pouches, and then shopping waste bags. So the shopping waste bags are made up of what? It's a blend of PLA, PHA, PBAT, and clear films for fruits and vegetables. We are covering it with the fruits and vegetables are normally covered with the clear films, and they are made up of PLA with a blend of PLA bio PET, and tea bags are nothing but what? PLA blends. So PLA is commercially used in many of the applications we are using them. Okay, and PLA properties for films for food packaging applications includes they provide excellent mechanical strength, light transmission, transparency, rigidity. They are low cost. They have high stiffness and resilience, easily biodegradable, excellent barrier properties, and biocompatibility. But it is brittle, has low melting strength, and low thermal stability. The properties of the PLA are excellent in nature, except that it has few disadvantages like easily to brittle and melt, and has low thermal. Since it has low thermal stability, they will melt soon. So these are all the properties. The commercial applications are nothing but what? It is used used in the manufacture of caps, coffee and capsule and pouches manufacturing, bags like shopping bags, clear films for fruits and vegetables, and tea bags are manufactured by using this because of the nature of many, because good properties which it possesses. The next is called as polybutylene adipate terephthalate, that is PBAT. So polybutylene adipate terephthalate is an aliphatic aromatic copolyester obtained from the polycondensation of butanediol, adipic acid, and terephthalic acid. So this polybutylene adipate terephthalate is a polymer which is it is a aliphatic and aromatic copolyester. Okay, so aliphatic means it is long chain, and aromatic means it is cycled. Okay, like benzene rings, all these things are called as aromatic things. So it is formed by the condensation process of this polycondensation of this butanediol, adipic acid, and terephthalic acid. All together makes the PBAT. It has been used for applications in agriculture, food packaging, and biomedical areas. So PBAT has good mechanical and biodegradable properties. However, it has poor photostability, which leads to decline in mechanical performance during the application. Poor photostability means it cannot able to withstand the photosensitive light. Okay. Furthermore, it has high melt viscosity, low crystalline rate, low tensile strength, high production cost. Therefore, it is usually used in application with blended polymers, nanofilters, and other natural compounds. So it is used in application with the other polymer blends. It is not used is used as a single material. So blended products such as PBAT and PLA PBAT have been developed for China to improve the mechanical properties and production cost. It's a polymer material developed by China. Here they have blended what starch PBAT and PLA PBAT are mixed together to produce another polymer which exhibits the higher mechanical property than the other one. Next is polycaprolactone. So polycaprolactone is a biodegradable polyester with a low melting point of 60 degrees Celsius and a glass transition temperature of minus 60 degrees Celsius. So the melting point is low and the glass transition temperature is minus 60 in this case. It is prepared by the ring opening of polymerization of epsilon caprolactone. So it is produced by the chemical reaction. It's a polymerization reaction of caprolactone is used for the preparation of polycaprolactone. It has a poor mechanical and thermal property, which is highly soluble and excellent ability to form blends with other polymer material. So that means it is also not used separately, it is used as a blend. So blending packaging materials like PCL and PLA, thymol, carvacrol by using the solvent casting method. So thymol and carvacrol are nothing but the antimicrobial additive substances which are all used along with the packaging bioactive polymer materials. So it is used to prepare or used to manufacture only polymer blends. So the PCA PLA film is loaded with the thymol and carvacrol mixture, had the highest total polyphenol content and antioxidant activity, acceptable physical property, and the lowest release rate of the substances which is present inside this. So this blend of PCL, PLA, thymol, and carvacrol provides a very good property for the polymer material when it is used as a single polymer material. The next one is polybutylene succinate. So polybutylene succinate is a thermoplastic biodegradable aliphatic polyester formed by polycondensation reaction. So it is formed by the polycondensation of aliphatic polyester substances. It has a property like polypropylene with high crystallinity and good thermal and mechanical properties. So it has a very good property of like high crystallinity index is high, thermal and mechanical properties are good in this case. PBS has been used as an additive with the other biopolymers such as PLA. So this also cannot be used as a single entity. So it has to be blended with other things in this case. So the blended film of PBS and PLA was developed with the incorporation of carvacrol and thymol by the extrusion casting method. So the inclusion of active compounds like carvacrol and thymol increase the ductility and flexibility of the PLA PBS based active films. So when it combined with other packaging material, it is a very good packaging instead of using as a single packaging material. The next category is polyhydroxyalkanate. So the polyhydroxyalkanate is a biodegradable, intracellular, and biocompatible family of bacterial polyester. So it is bacterial derived polyester, which are produced by bacterial fermentation of sugar and lipids. So when sugar and lipids undergo fermentation process, polyhydroxyalkanates are produced. They have a similar mechanical and thermal property like the synthetic polypropylene. High crystallinity, high barrier and thermal properties are for it also has the same properties like polypropylene. The merits of PHA include good tensile strength, printability, flavor and odor, barrier properties, and temperature stability is there. So it has a high melting point. If it is a low melting point, they will melt away easily. So high melting point is there. The application of PHA is limited due to its high cost, because since it is arrived from the bacterial fermentation process, the cost of production of this type of polyhydroxyalkanates are higher when compared to that of the other type of polymer materials. So the different polymers of PHA have been produced by different substrates like poly-3-hydroxybutyrate, co-3-hydroxyvalerate is produced from starch, vinasse, ethanol stillage, and cheese whey, while PHBV is manufactured by using starch, vinasse, ethanol silage, and cheese whey. Okay, all these are all used for making this type of polymer material. While poly-3-hydroxybutyrate (PHB) is produced from molasses wastewater and date syrup. When you use molasses wastewater and date syrup, it undergoes fermentation and it produces the PHB, polyhydroxybutyrate, can be produced. Similarly, polyhydroxyvalerate (PHV) is produced from molasses wastewater. We can produce this polyhydroxyvalerate. So PHA is used for industrial applications such as pharmaceutical, medical products, cosmetics, agriculture, aerospace, and food packaging industry. We are using this PHA. So during industrial applications, the polyhydroxyalkanates can be used as a raw material or as a blend with other polymer material also. You can use them single polymer material, or you can blend them with other polymer material such as polylactic acid, PBS and PCL. PHA is used as a biodegradable packaging applications in bottles, containers, sheets, films, laminates, fibers, and coating manufacturing. We can use this PHA. And metabolics, US produces metabolics PHA blend, a blend of PHP and poly-3-hydroxy octanate for food packaging and additive applications. So metabolics is a brand name of the PHA polymer-based material, which is nothing but a blend of polyhydroxybutyrate and poly-3-hydroxyoctanate are used as a blend in this case of PHA, and that is from this the food packaging materials are being developed. Next one is polyhydroxybutyrate. Polyhydroxybutyrate is the most abundant polyhydroxyalkanate that is biodegradable, lipid-like biopolymer synthesized by different bacteria that has a rigid structure. So this is all the PHAs. If you see, polyhydroxyalkanates are nothing but what? They are all bacterially produced material, bacterial polyesters. Fermentation of the starch and then sugar and lipids results in the process of making bacterial polyesters that are all used for making what? PHBV and then PHB are made from this. The another category of this is called as PHB, polyhydroxybutyrate, is also made from the bacterial fermentation process. It is suitable for food packaging material since it is renewable, biocompatible, and has low oxygen and water vapor permeability and increased barrier property. This can be used very often, and this is renewable also because we are going to obtain this from bacterial fermentation process. So what are all the applications in food packaging of the bioactive synthetic polymers? So they are all used as antimicrobial packaging, incorporating antimicrobial agents like essential oils or bacteriocins into the polymer material, inhibit the growth of the microorganisms on food surfaces. Then antioxidant packaging, adding antioxidant compounds like vitamin E or plant extract to polymers prevent oxidation of in food products. Then controlled release packaging. Some packaging materials are designed with a controlled release mechanism, which will constantly deliver the bioactive components into the food substances. Then food quality monitoring. Here we are going to insert some sensors, indicators can be fixed on the surface, so that when there is a pH change or any changes occurs, that will intimate the quality of the food substances to the consumers or to the retailers. Then edible packaging, developing films of coating made from bioactive polymers that are safe to consume directly with the food product. So edible packaging are nothing but what, along with the packaging material, we can consume it. That will not, the consumers will not see the coating, because this coating is applied as a thin layer on the surface. You know very well that apples are coated with wax coating. Okay, so that wax coating is a they are using only, no, they are not using natural wax, they are using some artificial wax or something they are using, which is not advisable to consume. So instead of this, you can go for this type of edible packaging, edible coating method, which is easily digestible or degradable also. And this table gives you about the packaging material, bioactive packaging materials and their characteristics, mechanical property, thermal properties, and where it's been used are given in this table. So with this, we have completed it. Thank you. So